Greetings, and in today's video, I'm going to walk you through not one, but two different ways to prove Euler's formula. One using the traditional Maclaurin expansion, and the second method by solving a simple differential equation. But before we begin, let me give you a quick introduction to Euler's identity. You may have heard of Euler's identity, sometimes called the most beautiful equation in math, because it contains Euler's number. And one useful property that number has is that the differential of e to the power of x gives us e to the power of x. It also contains the imaginary number, where when I is squared, it gives us -1. And it also has pi, the ratio of a circle's circumference to its diameter. And when we add 1 to this will give us 0. Now, to prove Euler's identity from the formula, we only need to substitute theta equals to pi. And since we know that cosine of pi gives us -1 and sine of pi gives us 0, this proves Euler's identity. Now, the question becomes, how do we prove Euler's formula? So first, we need to understand where the right-hand side comes from. And this is done by considering a point on the Argand diagram. Now, an imaginary number z can be represented as a point on an Argand diagram at the coordinate x, y. Now, for our purposes, this point will lie on a unit circle with radius 1 centered on the origin. In polar form, we can assign this point z a principal argument of theta, which is the angle that the point makes with the positive real axis. By dropping a vertical line from z, we can construct a triangle. And using basic trigo ratios, we know that the height is equals to sine of theta, and the base will be cosine of theta. Hence, any point on the unit circle can be represented in the form of cosine theta plus I of sine theta. So before we go into the polynomial series proof, we need a quick recap. So firstly, the general idea of Maclaurin is that it rewrites a function of x into an infinite polynomial series, otherwise a0 plus a1x plus a2x squared, and so on and so forth. Now let's take the example of sine x. So we can find a0 by just substituting x equals to 0. So when x equals to 0, a0 is equals to sine 0, and that tells us that a0 equals to 0. Now to find a1, we differentiate both sides. So this time we'll have cosine x equals to a1 plus 2a2x and so on. And again, we substitute x equals to 0. This will tell us that a1 equals to cosine 0, and that tells us that a1 equals to 1. So we just keep repeating this process of differentiating both sides and substituting x equals to 0 ad infinitum. So for sine x, this is the polynomial series that we'll eventually get. We can replace all the x with theta, and we're going to multiply I throughout the entire series. Next, we repeat again, but this time for cosine x, and again, we're going to replace all the x with theta. And again, for e to the power x, this is the Maclaurin series expansion, and we're going to substitute all the x with I theta. And this is what we get. After opening the brackets and simplifying the expansion for e, notice that every term in the expansion for e to the power of I theta can either be found in the I sine theta expansion or the cos theta expansion. In fact, what you'll observe is that every even powered term is from the cosine expansion, and every odd term is from the sine expansion. Hence, the sum of I sine theta and cos theta gives us e to the power of I theta. Now, the Maclaurin series proof has always been a bit mysterious to me because while it makes logical sense, it doesn't fully explain why exponential functions have to be involved here. So I'm going to present to you an alternative proof that hopefully makes more intuitive sense. So again, we start from the right-hand side, and we're going to differentiate both sides. So differentiating cos theta gives us negative sine theta, and differentiating sine theta gives us cos theta. Next, we can factorize out an I, and notice that you'll get I times, in brackets, I sine theta plus cos theta, which is exactly the z that we started off with. In other words, it gives us I multiplied by z. And this, you might recognize, is a simple differential equation that you might have already solved before. So how you solve it? You bring the z down to the left-hand side and you bring the d theta up to the right-hand side. And we integrate both sides. So integrating 1 over z with respect to z gives us ln z. And integrating I with respect to theta gives us I theta. Unfortunately, life is not that perfect. We have to remember to add the constant of integration. So if we make z the subject, now we have z equals to e to the power I theta plus c. So voila, the e has shown up. All we need to do now is to show that the c equals to 0. So to find c, we can just let theta equals to 0, which from the Argand diagram is just this point on the unit circle. It's just z equals to 1. Next, we substitute theta equals to 0 and z equals to 1, and that will show us that c equals to 0. And that essentially concludes our proof. We have come to the end of this video. I hope it has given you some new insights into Euler's formula and Euler's identity. Thank you and have a good day of learning.